In this video, we're going to start learning about the gas laws. Gas laws are mathematical. They will describe how gases behave. Gas behavior can be predicted by theory, but the amount of change can be calculated with mathematical equations. So you're going to need to know both. And you're going to need to know the theory of how gases behave and why, but you also need to be able to do the math, which is what I'm going to teach you next. So our first gas law is called Boyle's law. And it says that gas pressure is inversely proportional to the volume when temperature is held constant. We've already learned this, that the pressure and volume are indirectly related to one another. When the volume is high, the pressure is low. But if we decrease the volume, we increase the pressure. Now mathematically it looks like this. P1 times V1, this means our initial pressure times our initial volume, is equal to our new pressure, P2, times our new volume. So this is what the Boyle's law would look like graphically, but we're going to solve an example problem here. So a balloon contains 30.0 liters of helium gas at 103 kilopascals. What is the volume of helium when the balloon rises to an altitude where the pressure is only 25 kilopascals? Assume the temperature remains constant. So we know it's a Boyle's law because I've written on top that it's a Boyle's law example. But if you see units like liters and pressure, and we're changing to a new pressure, what's the new volume, and they are not talking about temperature at all, temperature is remaining constant, that should be ringing bells that this is a Boyle's law example. So we would use this formula, P1 times V1 equals P2 times V2. So in our word problem here, it says that the balloon contains 30 liters. That is our initial volume. And that gas is at 103 kilopascals. Now, kilopascals is a unit of pressure, so that's our initial pressure. So that's what we'll go here. They're asking what's the volume going to be. So they're asking for V2 when the balloon rises to an altitude where the pressure is only 25 kilopascals. So they're changing the conditions of the pressure. It's going from 100.3 kilopascals to 25 kilopascals. And they want to know what's the new volume going to be. So once you plug all this in, this should be rather simple. The math for this chapter is very simple, but you need to be able to cross multiply and isolate variables correctly. So I want to get V2 by itself. So to do that, I'm going to divide both sides by 25.0 kilopascals. Now the 25 and the 25 will cross off on the right and leave me with V2. So V2 is going to be equal to 103 kilopascals times 30.0 liters divided by 25.0 kilopascals. Now I like to write the units like I did here because I can see that kilopascals and kilopascals will cancel. I'm left with liters, which is a unit of volume, so that tells me that I've probably set it up correct. It's time to go to the calculator. So in my calculator I would type in 103 times 30, enter, divided by 25. Now be careful doing this all at once in your calculator. Some people might type in 103 times 30 divided by 25, like if we were doing a stoichiometry problem. And what that's going to do is it's going to do 103 times whatever 30 divided by 25 is, which is what you don't want to do. So you need to be savvy with your brackets, or just hit enter after every line. 103 times 30, enter, divided by 25. Or you could do open bracket, 103 times 30, close bracket, divided by 25, enter. Your choice, but this is a pretty easy math problem. Don't mess it up by pushing the calculator buttons incorrectly. So if you do it correctly, your answer will be 124 liters. Our next gas law is called Charles' law. And it says that the volume of a fixed mass of gas is directly proportional to the Kelvin temperature when pressure is held constant. So one of the problems with Charles' law is that you need to use temperature, and in this chapter temperature always needs to be in Kelvin. So you need to convert whatever Celsius temperature they're most likely going to give you in the problem to Kelvin. So this is on table T. You do not need to memorize these formulas. You probably will because it's not hard to memorize. But the Kelvin is whatever the Celsius degree temperature is plus 273. If we needed to go the other way, the formula is also on table T. It's the Kelvin temperature minus 273. So let's look at an example problem here. A balloon inflated in a room at 24 degrees Celsius has a volume of 4.00 liters. The balloon is then heated to a temperature of 58 degrees Celsius. What is the new volume if the pressure remains constant? So we will use Charles' law here. We will start with the formula and we'll plug in the variables that they give us. So the first thing we need to do is find the T1. So it says that the balloon is at 24 degrees Celsius initially. So we take 24 degrees Celsius and add 273, and that is 297 Kelvin. We'll plug that in for T1. And that balloon inflated at that temperature has a volume of 4.00 liters. So we'll plug that in for our V1. The balloon is then heated to 58 degrees Celsius. We need to find out what that is in Kelvin. So our T2 is 58 degrees Celsius plus 273. That is 331 Kelvin. And they want to know the new volume, so that's what we're solving for, V2. Okay, so in order to solve for this, we need to cross multiply. So I'm going to do 4.00 liters times 331 Kelvin. That's cross multiplying this way. You could have gone this way first, it doesn't matter as long as you do both. And that is going to be equal to V2 times 297 Kelvin, just cross multiplying this way. So next we need to isolate our variable V2. We're going to divide both sides by 297 Kelvin. 297 divided by 297 on the right will cancel out. And V2 is going to be equal to 4.00 times 331, enter, divided by 297. The Kelvins cross off, I'm left with liters, which is a unit of volume, so that's probably set it up correct. And your answer, if you type this in correctly, is 4.46 liters. The last one is this guy's law. It says that the pressure and Kelvin temperature of a gas are directly proportional provided that the volume remains constant. So mathematically it looks like this. P1 over T1 equals P2 over T2. Remember, it's Kelvin temperature, so if you have any Celsius temperatures in the word problem, you need to convert them first or you're going to get the question wrong. This law is also what kind of describes why pressure cookers work so well. So at higher pressures, you can get water to higher temperatures. Remember from last chapter, when we boil water, we reach that heat of vaporization, and the water only boils at 100. You can't get a boiling pot of water any hotter than 100 degrees Celsius at standard pressure. But if we use this pressure cooker contraption, we can create higher pressures inside of this container, and we can cook food at temperatures higher than 100 degrees Celsius and cook it faster. So here's an example problem. If a gas in a closed container is pressurized from 15 atmospheres to 16 atmospheres, and its original temperature was 25 degrees Celsius, what would the final temperature be? So you see I'm using a different pressure here. I'm using atmospheres in this example rather than kilopascals. It makes no difference. As long as your units are the same, you can use them. The only one that you need to do a conversion for is temperature. Okay, so let's set this one up. So we're going to use this formula, P1 over T1 equals P2 over T2. And we need to start plugging in the variables from the word problem. So the gas is pressurized from 15 to 16 atmospheres. So my P1 is 15 and my P2 is 16. It says the original temperature was 25 degrees Celsius, but remember we can never use Celsius, so we need to convert that to Kelvin. So 25 plus 273 is 298 Kelvin. And we want to know the final temperature, so they're asking us to solve for T2. So again, we need to cross multiply. So we'll do 15 times T2 is equal to 298 times 16. We're going to isolate that variable T2 by dividing both sides by 15 atmospheres. 15 atmospheres divided by 15 atmospheres will cancel out. Our units will cancel out as well. Atmospheres and atmospheres will go away. I'll be left with Kelvin, which is a unit of temperature, so that's good. And my math is just 298 times 16 divided by 15, and that's 318 Kelvin. So in summary here, the gas laws are a mathematical way of predicting and describing gas behavior when a variable changes. The challenge with gas law problems is setting them up. You need to be able to read the word problem, pick out the variables, and plug them in correctly. You also may have an issue with knowing which formula to use and when. You also are going to need to cross multiply, and I see a lot of problems with this, surprisingly, in my classes. The students not cross multiplying correctly. If you need help with cross multiplying or extra practice, please let me know. So far we've learned 3 gas laws, but you actually don't need to memorize them, because in the next video I'm going to show you a gas law that contains all of the other gas laws into one. It's the only gas law that's on your reference table. So if you start with this one gas law, you're going to be able to convert it into all the other 3 that we just did. So tune in for that video and I'll show you how that's done.